These examples go with lesson 10.2, tests for independence and homogeneity. Example 1. The following contingency table presents observed frequencies. Compute the expected frequencies. Okay, we need our formula for computing the expected frequencies. It is the row total times the column total, and this is divided by the grand total. All right. So let's have us a total column out here and a total row down here. And we'll add up each of the rows across. So 13 plus 8 plus 27 and get our total. And then 18 plus 21 plus 35 and get our total. And then down here we'll add 13 plus 18 plus 19 plus 20 and get our total. And you can see I've filled in the totals over here on the side. This is the total of row A, row B, row C, row D. Down here, the 233, this is the grand total. This is the sum of all of my row totals. Down here, we have the total of column 1, column 2, column 3. And again, the grand total is also the sum of all of my column totals over here. So this is a good way to check yourself and make sure you've added correctly. It needs to add to be the same this way as well as this way right here. Okay, now let's go and find the expected frequencies. And here we're going to have 12 because there are 12 cells in our contingency table here. All right, and the way I like to do this is row A, column 1. So we are computing for this one right here. That means I'm going to be using the row total 48, the column total 70, and then the grand total, of course, is going to be the 233. All right, so the expected frequency for A1 is going to be 48 times 70 divided by 233. And if we round that off to one decimal place, it's going to give us 14.4. Okay. Let's take that off, and take that off, and take that off. Now where you go next is up to you. We can go over here and do A2, or we can go down here and do B1. It really doesn't matter. We're going to have to do all 12 of them anyway. And I'm just going to go B1, sorry, because I'm just going to do this whole column and list them one underneath the other right here. All right, so if we're doing B1, that means we're going to need the row B total, which is 74, times the column 1 total, which is 70, and then that's going to be divided by the grand total of 233. And we'll put this in the calculator and round it out to one decimal place. And that looks like it's giving me 22.2. All right, for C1, we're going to take those off. Let's get rid of that one. Oops. And that one. All right. Now we're looking at row C. 47 is the row total. Column 1, 70 is the column total. 47 times 70, and this will be divided by 233. And we'll put that in the calculator and round it off to 1 decimal place. And that looks like it's giving me 14.1. And then finally, we'll finish out column 1 with D1. Take this out of here. Now I'm looking at row D. 64 is my total. Column 1, 70 is my total here. Therefore, D1 is going to be 64 times 70 divided by 233. And we'll put this in the calculator and round it out to 1 decimal. And this is giving me 19.2. All right, now, why don't you go ahead and pause the video and find the expected frequencies for column 2 and for column 3. And then I'll go ahead and put them up here, and you can check your work against mine. Okay, and over here to the side, these are the expected frequencies I got for column 2, and these are the expected frequencies I got for column 3. I hope you did well. Example 2. The following contingency table presents observed frequencies. Part A, compute the expected frequencies. All right, in order to do this, we're going to need to have our row totals and our column totals. And then, of course, right here, we're going to need to have the grand total. So let's calculate those. Okay, so now I have my row totals over here on the side, and I've got my column totals down here underneath, and the grand total right here of 163. Now I need to compute all of the expected frequencies, and it looks like, once again, I'm going to have 12 of them to calculate. All right, so I'm going to start with cell A1, and row A had a total of 35. And column 1 had a total of 61. And then the grand total was 163. And when we put this into the calculator, and we round to 1 decimal place, we get about 13.1. All right. So why don't you pause the video and go ahead and find the other expected frequencies, and then cut it back on and check yours against mine, and let's see if we got the same thing. Okay, and I have all of the expected frequencies calculated out around here. Here is row A across the top, and then row B right here underneath it, row C right here down the side, and then row D down here on the bottom. Part B says one of the observed frequencies is less than 5. We're talking about this one right here. Is it appropriate to perform a test of independence? Well, remember, we can perform the test of independence as long as all of our expected frequencies are more than 5. And if we go back and look at all of our numbers up here that we just calculated, all of these are greater than 5, so we're okay. So we can say yes to this one because all expected frequencies are greater than or equal to 5. And we're good to go. All right, part C is asking us to compute the value of the test statistic, okay, our chi-squared. Now remember, to get to the chi-squared, we're going to have to add together all of the old minus the expected squared divided by the expected. All right, and I'm going to have to get a clean slide to put all that on there because I don't have any more room for this. So let's bring up a clean slide. All right, so here's our formula once again. To get to the chi-squared, we're going to have to add together all of our observed frequencies minus our expected frequencies, and we're going to have to square that divided by the expected frequency. All right, and remember we had 12 observations in there. So we're going to have 12 of these little fractions to add together. So let's take a look at this. All right, in cell A1 was 8, and the expected frequency for A1 was 13.1. And we're going to have to divide that by 13.1. Plus, in cell A2, was the number 13. And the expected frequency that went with that was 10.7. And we're going to divide this by 10.7. And in cell A3 was the number 14, and its expected frequency was 11.2. And we're going to divide this by 11.2 plus, and now we can do cells B1, B2, and B. All right, the observed frequency in cell B1 was 18, and its expected frequency was 12.7. I'm going to square that and divide it by 12.7 plus the observed value in cell B2, this was 1, and we're going to subtract the expected frequency, which we got to be 10.4. I'm going to square that and divide by 10.4 plus, all right, the observed value in cell B3 is 15, and the expected frequency for B3 was 10.8 squared, and we're going to divide that by 10.8. And now I'm going to continue down here, and I'm going to do row C and then row D. All right, so here's what our equation looks like once we have all of the observed minus expected squared divided by expected set up. And we're going to add all these together, so let's put all this in the calculator, and whatever we come up with is going to be our chi-squared test statistic. All right, and when we put all this in the calculator and calculate it, it's giving me 21.0541. So there is our chi-squared statistic. Okay, let's go back to our problem. Part D, how many degrees of freedom are there? Okay. Well, the degrees of freedom, the formula was the number of rows minus 1 times the number of columns minus 1. And so in this case, we had 4 rows and 3 columns. Right, so 4 rows minus 1 times 3 columns minus 1. That's going to give me 4 minus 1 is 3, 3 minus 1 is 2, so 3 times 2, we have 6 degrees of freedom for this problem. Okay. And then for part E, are we going to reject a null hypothesis at the alpha equals 0.05 level? Okay, so we need to pull up table A4. We're going to be on line 6 for 6 degrees of freedom, and then the 0.05 column. All right, so let's pull up table A4. All right, here's our table A4, column 0.05, and we need to go down to line 6. I believe that's right here, where our critical value is 12.592. Critical value is 12.592. All right, now if we look at a picture of this, we've got our chi-square curve right here. And we know at this point, 12.592, all of this area back here is 0.05. And we want to know where our chi-square statistic falls, 21.05. That's going to be way back here. It is way beyond our 12.592. So that means that we will reject the null hypothesis. And the reason we're going to reject the null hypothesis is because our test statistic here, the chi-squared, is greater than our critical value. So we're going to reject it because 21.0541 is greater than 12.592. Oh, I forgot to put at the alpha equals 0.05 level. And what we've said in the past is the fact that because our test statistic falls in the shaded area, we're going to reject the null hypothesis.